Hello friends, welcome back to my YouTube channel. In this class, I am going to discuss 3 more problems of chapter 7 of P.K.NAG's Engineering Thermodynamics, which are based upon the concept of entropy and entropy generation. The question numbers 7.19, 7.20 and 7.21 I am going to discuss in this lecture. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. So question number 7.19 is like this. For a fluid for which P small v by T, in fact this small v is specific volume, is a constant quantity equal to R, so that the change in specific entropy between two states and B is given by SB minus SA. This is change in specific entropy, integral of Cp by T dt, and limit is from Ta to Tb minus R ln Pb by Pa. A fluid for which R is constant and equal to 0.287 kilojoule per kg Kelvin. In fact, this value of R is that of air, we know. So definitely it is air that flows steadily through this adiabatic machine. Flows steadily through an adiabatic machine, entering and leaving through two adiabatic pipes. In one of these pipes, the pressure and temperature are 5 bar and 450 Kelvin, and in the other pipe, pressure and temperature are 1 bar and 300 Kelvin, respectively. Determine which pressure and temperature refer to inlet pipe. For the given temperature range, Cp is given by A ln T plus B, where T is the numerical value of the absolute temperature, and A is equal to 0.026 kilojoule per kg Kelvin, and B is equal to 0.86 kilojoule per kg Kelvin. Suppose A is, this pressure and temperature condition refers to suppose A. So A, this is suppose section A. Here pressure is 5 bar and temperature is 450 Kelvin, and at section B, suppose the pressure and temperature are 1 bar and 300 Kelvin respectively. So pressure is 1 bar and temperature is 300 Kelvin. So how to find out which one is inlet section? Which pressure and temperature refer to inlet pipe? Supposing that A is the inlet and B is the outlet, and in the process we will calculate SB minus SA, that is change in entropy of the system. In fact, we want to calculate the change in entropy of the universe, and in this case, you know, the pipe is, this machine is an adiabatic machine, so no heat flows towards the surroundings, nor any heat flows from the surrounding to this pipe, so that the change in entropy of surrounding is here 0, because no heat interaction takes place between system and surroundings, because the machine is adiabatic. So delta S universe is here nothing but the delta S of this system. So if this is the initial state inlet section and this is outlet section, if you calculate SB minus SA, and if it comes out to be positive, then this is a feasible process, because according to the principle of increase of entropy, delta S universe has to be greater than or equal to 0. So it cannot be negative. If suppose this comes out as negative, means this process is not feasible, and in this case the delta S universe is nothing but equal to delta S of system, that is the pipe. This is the entropy at section B minus entropy of section A we will calculate, and if it comes out to be 0, then greater than 0, then section A will become inlet and section B will be outlet. And if it becomes negative, then this will be inlet and this will be outlet, because any for any process to occur, delta S universe cannot be negative. So if it comes out to be negative, means this process is not feasible. This flow from section A to section B is not feasible, and for reverse case is possible. So flow can take place, but from B to A, not from A to B. So we'll check it. So first our objective is to find out the SB minus SA. For that, we can use this. Actually comes from one of the property relations. This expression comes from property relations, that is TDS equal to DH minus small vdp. This is in fact specific entropy, change in specific entropy. This is specific volume. This is in fact a property relation. From this we can obtain ds equal to dh divided by t minus v by t dp, and this is equal to dh is equal to cp dt divided by t minus r dp by p. You know, Cp is here A plus ln t. Cp is given to be, A ln t plus B. So, in place of Cp, we can write A ln t plus B divided by t dt minus r dp by p. If you integrate between two limits, that is SA is the initial state and SB is the final state, this will be A ln t upon t dt. Limit is from TA to TB plus B dt upon t, TA to TB minus R ln P. If you integrate dP by P, it will be ln P. Limit is from PA to PB. This will be, on integrating, this is SB minus SA. These are specific entropy per unit mass. This is A ln T one by T dt plus B integration of dt upon T is ln T. Limit is from TA to TB minus R ln PB upon PA. Taking ln T is equal to, suppose Z, we know that derivative of ln T is 1 by T. So 1 by T dt is equal to dz. So our expression SB minus SA now becomes A. In place of ln T I will take Z, and in place of 1 by T dt I will take dz. Accordingly the limit will change. Ln TA will be one limit and ln TB will be another limit. Then plus B ln TB upon TA minus R ln PB upon PA. So this is equal to A Z square by 2 ln TA, this is ln TB plus B ln TB upon TA minus R ln PB upon PA. So this is equal to A by 2. 1 by 2 can be taken outside. This is ln TB square minus ln TA square plus B ln TB upon TA minus R ln PB upon PA. So by putting the values of A and B and TA and TB, we will get this is equal to 0.026 divided by 2 ln 300 square minus ln 450 square plus 0.86 ln 300 by 450 minus 0.287 ln 1 upon 5. So this is minus 0.062261 minus 0.348699 plus 0.461897. This becomes plus 0.0509 kilojoule per kg Kelvin. So this is delta S of system. So delta S of universe, change in specific entropy of universe will be 0.0509 plus this is the change in specific entropy of this system, plus we know that delta S of surrounding is 0 because this is an adiabatic machine. So this is 0.0509 kilojoule per kg Kelvin, which is greater than 0. Hence this process is feasible. This flow, in fact, this flow from A to B is possible. Since this is a possible process, according to the principle of increase of entropy, delta S universe has got to be greater than or equal to 0. And the flow is from A to B. So A is the inlet pipe. A is the inlet pipe and B is the outlet pipe. A is the inlet pipe. So this one is the inlet. So A is the inlet pipe. This one, section A, is the inlet one. Because we calculated SB minus SA and it came out to be positive, so that the process is feasible, because the SB minus SA is nothing but equal to delta S universe for this process, and if it is greater than 0 means this process is feasible. So the flow is possible from A to B. So A is the inlet section. That means inlet pressure is 5 bar and outlet pressure is 1 bar, and inlet temperature is 450 Kelvin, outlet temperature is 300 Kelvin. So next question, 7.20 question is like this. Two vessels A and B two vessels A and B, each of volume 3 meter cube. 3 meter cube may be connected by a tube of negligible volume. Vessel A contains air at 0.7 megapascal 95 degrees Celsius, while vessel B contains air at 0.35 megapascal 205 degree Celsius. Find the change in entropy when A is connected to B by working from the first principle and assuming the mixing to be complete and adiabatic. For air, take the appropriate relations. So there are two vessels, vessel A and vessel B. Suppose this is your vessel A, this is vessel A, 0.7 megapascal, 0.7 megapascal मतलब 700 kilopascal, and temperature is 95 degrees Celsius means 368 Kelvin. Air is contained in this vessel A and this volume is also 3 meter cube. So another vessel of volume 3 meter cube is also there. This is another vessel, vessel B. Pressure here is 0.35 megapascal, 0.35 megapascal, and temperature is 205 degrees Celsius means 478 Kelvin. Cp is given to be, for air we know Cp is 1.005 kilojoule per kg Kelvin. Cb is equal to 0.718 kilojoule per kg Kelvin. And of course R is the difference between the two. R is 0.287 kilojoule per kg Kelvin. And this process is adiabatic. So you see, we have to find out the change in entropy. Change in entropy of, in fact, in universe. Total change in entropy of universe during the process we are to calculate. You see, first we will apply energy balance principle. Any problem based upon the concept of entropy can be solved by applying two principles of balance. One is for energy balance principle and the other one is entropy balance principle. So if you apply energy balance principle and if you consider this as the whole system, or which consists of these two subsystems, suppose two subsystems. So you see, if you apply the energy balance principle, that is E in minus E out is equal to delta E. If suppose E in is the summation of energy that enters into a system during a process and E out is the summation of energy leaving the system during that process, then net energy will be accumulated in the system itself. So if you apply this to this combined system, you will see that here no energy enters, so E in is 0 and E out nor any energy also leaves the system. If you consider this as a combined system for analysis, then delta E is equal to 0. Delta E is nothing but summation of delta Ek plus delta Ep plus delta U. Delta U is molecular internal energy, change in molecular internal energy, 0. But here it is obvious that there is no change in kinetic energy, there is not any change in potential energy, so these two terms are 0. So now delta U is equal to 0. Delta U, you know, internal energy is an extensive property or additive property. So delta UA plus delta UB is equal to 0. Change in internal energy of vessel A plus change in internal energy of vessel B is equal to 0. So what is the change in internal energy of vessel A? You know, for an ideal gas, internal energy is a function of temperature. When the vessel A mixes with vessel B through a pipe whose volume is negligible, then what happens? An equilibrium temperature will be attained. Its temperature will go down and its temperature will go up because this temperature is higher than this temperature. So if you calculate, let Tf be final temperature, final equilibrium temperature just after the mixing has taken place. So then we can apply the equation Ma CVA Tf minus 368. If the temperature of this vessel A rises to 368, then change in internal energy will be this much. Rises to Tf, in fact. This temperature will increase and this temperature will decrease. So for vessel A, this is the change in internal energy. And for vessel B, change in internal energy will be, in fact, 478. In fact, the final temperature will be Tf minus 478. So this will be 0. And this can be written as MaCVA Tf minus 368 equal to minus MbCVB Tf minus 478. This is equal to Mb, mass of vessel B, 478 minus Tf. 478 minus Tf. So you see, this is same for both the vessels because both vessels contain air. Both vessels contain air. So Cv for this air is same as Cv for this air in the vessel B. The Cv value is, for both the cases, Cv is 0.718. So now the equation is like this. But you have to find out mass of vessel A, mass of air contained in the vessel A, and mass of air contained in the vessel B, so that we can find out the equilibrium temperature. You see, mass of vessel A is nothing but ideal gas. From ideal gas equation, Pa Va divided by RTA. This is equal to 350 multiplied by 3 divided by 0.287 multiplied by 4. TA is 368. From this, mass of A is 19 point. So pressure is, in fact, this is 0.7 megapascal for vessel A. So 0.7 megapascal is 0.7 megapascal is 700 kilopascal. So this is 700 multiplied by 3, and on dividing it comes out to be 19.88335 kg. And for mass of vessel B is PB, VB, RTB, and this is equal to 350.35 megapascal is 350 kilopascal, and VB is same as VA, that is 3, R is 0.287, and TB is 478. So this is equal to 7.653842 kg. So now putting these values of MA and MB in the equation that we obtained, we can get the value of TF, final equilibrium temperature. So that equation is 19.88335 multiplied by 0.718 multiplied by TF minus 368 equal to 7.65384 into 478 minus TF, of course 0.718 is there. These two terms cancels out. Now on equating this, we get 19.88335 TF plus 7.653842 TF is equal to 10975.6092. From this, 27.5371 TF is equal to 10975.6092. TF is equal to 398.575 Kelvin. So we can obtain the final equilibrium temperature after the two vessels, air in the two vessels have mixed with each other. Then we can find out the equilibrium temperature from the ideal gas equation, that is PF Vf is equal to MF R TF after just mixing has taken place. So MF is nothing but MA plus MB. This is 27.5372 kg. So Vf is equal to MF RTF. From this, Pf is equal to 27.5372 multiplied by 0.287 multiplied by 398.575 TF divided by Vf is here 6, because after the mixing has taken place, the two vessels will mix, the air in the two vessels will mix with each other, so volume will become 6 meter cube in place of 3 meter cube, because after mixing this will be the volume for the final, after the mixing the volume will be 6 meter cube. So Pf is 525 kilopascal, 525 kilopascal. So 525 kilopascal. So now we have to calculate change in entropy of universe. For that, entropy is an additive property. For vessel A and vessel B, we can find out the change in entropy individually, then add them, then finally we can get the delta S universe, because delta SA plus delta SB is the here delta S universe, because since it is a adiabatic process, so delta S surrounding is here 0, because there will be no heat interaction between this system, this composite system. This is an adiabatic process. So only delta S universe will be nothing but delta S of this subsystem A and plus delta S of this subsystem B, and the delta S of surrounding will be 0. So we are to calculate just delta SA and delta SB, then add them to find out the delta S universe. Delta SA, this vessel A contains air. For air, the change in entropy of ideal gas formula we have to apply. So this is equal to MA Cp ln TB upon, this is in fact TF. TF is the final temperature, minus R ln PB upon PA. So for the change in calculating the change in entropy of ideal gas, these two property relations are used as per requirement. TdS is equal to dH minus VdP, or TdS is equal to du plus VdP. Here this property relation has been used, from which delta SA 19.88335 multiplied by 1.005 ln TF is 398.5 divided by 368 minus 0.287 ln 525 divided by 700. This is equal to 3.3277 kilojoule per Kelvin. Similarly, delta SB, same formula can be used. MB Cp ln TF upon TB minus RLN PF upon P. This is in fact PF. The final expression, final pressure will be written. So PF divided by PB. So this is equal to, just by putting all these values, it will come out as minus 2.28795. Now delta S universe is equal to, entropy is an additive property, delta S A plus delta S B plus delta S surrounding. This one is 0 since this is an adiabatic vessel, adiabatic mixing process. So this is equal to 3.3277 minus 2.2879 is equal to 0.9498 kilojoule per Kelvin. 0.9498 kilojoule per Kelvin. So this is a feasible process, and in fact this is an irreversible process. Whenever delta S universe of a process is greater than 0 means this is an irreversible process. So next question is 7.21. You see, an aluminium block with a mass of 5 kg is initially at 40 degrees Celsius in a room air at 20 degrees Celsius. It is cooled reversibly by transferring heat to a completely reversible cyclic heat engine until the block reaches 20 degrees Celsius. The 20 degrees Celsius room air serves as a constant temperature sink for the engine. Compute the change in entropy of the block and the change in entropy for the room air and the work done by the engine. And in the second part is like this: if the aluminum block is allowed to cool by natural convection to room air, compute the change in entropy for the block. Second is change in entropy for the room air and the net change in entropy of the inverse. First part is a reversible process, while second part is an irreversible process, because the heat transfer takes place through finite temperature difference. Finite temperature difference. You see, so an aluminum block is there. For the first part, an aluminum block is there whose temperature is, see, aluminum block whose temperature is 40 degrees Celsius, and the room air here is, room air is at 20 degrees Celsius, and suppose this is your capital T and this is your T1, and this is 293 Kelvin. 20 degrees Celsius means 293 Kelvin, and this is 313 Kelvin. And Cp value is given 400 joule per for aluminium 400 joule per kg Kelvin, and mass of block is given to be 5 kg. So a heat engine is there which produces some work with the expense of this heat that flows from block to room because of the temperature difference. So this is the heat Q, and this work is produced by this heat engine. This is heat engine, and if this is Q and this is W, then this is Q minus W. Here there is a heat engine, cyclic device. So first we have to calculate delta S of, or change in entropy of aluminium block. Change in entropy of aluminium block. You see, delta S of block is nothing but mCp dt upon T, and the limit is from initial temperature of block is 313 and final temperature is 293, 20 degrees Celsius. Because eventually this process will continue, this production of work by the reversible heat engine will continue up to the point when the temperature of block goes down and becomes equal to 20 degrees Celsius. Because whenever heat flows to room air, the temperature of room air will not increase. In fact, it will act as a thermal energy reservoir. Only the temperature of block will go down up to 20 degrees Celsius. So, because heat will flow from block to room air, mCp can be taken outside because they are constant. So, this is mCp ln 293 divided by 313, and this comes out to be minus 132.0611 joule per Kelvin. And delta S for room air, is plus 132.0611 joule per Kelvin. Because delta S of heat engine is always 0. So if you calculate delta S of universe for this whole process, you see this is a reversible. All the processes that occur in this case are reversible. According to principle of increase of entropy, delta S of universe is equal to 0 for reversible process. So here this plus this has to be 0. Since this we have already calculated to be minus 132.0611, hence delta S of room air has to be plus 132.0611, so that summation will be 0. Delta S universe will be 0. So now we have to calculate, in fact, to find out the work, we need to calculate Q. Q is mc T1 minus T, because this is the heat rejected. You see, this is the heat rejected by the block. So this heat is nothing but mc T1 minus T. So this is equal to mc T1 minus T, and this is equal to 5 into 400 into 40 minus 20, and this is equal to 40,000 joule. So if you calculate the change in entropy of, this is a thermal energy reservoir, what will be the change in entropy of this thermal reservoir in terms of Q and W? Delta S of room air in this case is nothing but Q minus W divided by 293, and Q is 40,000 minus W is W we want to calculate, and this is already we have calculated delta S of room air 132.0611 joule per Kelvin. So on equating these, we can find out W. So W is equal to 1306.09 joule. On equating this, delta S of room air already we have calculated. So from this, in fact, W can be calculated, that is 1306.09 joule. But what about the bit B? You see, if the aluminum block is allowed to cool by natural convection to room air, compute the change in entropy of block, change in entropy for the room air, the net change in entropy of the universe. This is a case of an irreversible heat transfer from block to natural air. Suppose aluminum block is here, whose temperature is 40 degrees Celsius or 313 Kelvin. In fact, mass is same and Cp is also same. Mass is 5 kg, Cp is 400 joule per kg Kelvin. So heat will flow directly to room air through mode of natural convection. No work is produced. Room air temperature of room air is 293 Kelvin. So now this is Q. So as far as the change in entropy of block is concerned, this will be same as it was in the first part, because the same change in temperature is there, and temperature drops from 40 to 20 degrees Celsius. So delta S of aluminum block will be same as it was in the part A. This is equal to mc dt upon t, and limit is from 313 to 293. So this is equal to 5 into 400 ln 293 divided by 313 minus 132.0611 joule per Kelvin. So in this case, delta S of room air will be nothing but delta S of room air. You see, delta S of room air is just whatever heat Q is rejected by this block to the room air divided by the temperature of room air. Here the room air acts like a thermal energy reservoir. It does not change. So for room air, delta S of room air will be plus Q upon T, and Q already we have calculated in the first part, and this is 40,000 joule. 40,000 joule divided by 293 Kelvin. This is equal to 136.518 joule per Kelvin. So this is plus and this is minus. So delta S universe is equal to, and delta S of the universe here consists of these two parts. So delta S universe is equal to minus 132.0611 plus 136.518 joule per Kelvin. This is equal to 4.45 joule per Kelvin. And you know that when delta S universe is greater than 0, it is an irreversible process. And you know, this is also an irreversible process, as we know, because heat transfer here takes place through finite temperature difference, because the temperature of block is 40 degrees Celsius and temperature of room air is 20 degrees Celsius, and there is a finite temperature difference. So obviously this is an irreversible process. So that's why delta S universe has come out to be positive, because according to principle of increase of entropy, delta S of universe has to be greater than or equal to 0, greater than 0 for irreversible process and equal to 0 for reversible case. So in the first part, that was an example of reversible process. So that's why delta S universe was 0. But in this case, it will be greater than 0. That's all, and Thanks for watching.